discuss about one of the significant topics in the geomorphology, that is isostasy. After completion of this lesson, you will be able to understand the concept of isostasy as well as different theories in isostasy. Let us have an introduction. Isostasy, though often overlooked as a geological force, it plays a crucial role in shaping Earth's surface. It governs the vertical movement of the crust in response to loading and unloading such as erosion, sedimentation, glaciation or tectonic activity, thereby significantly influencing long-term landscape evaluation and elevation changes. As we know, Earth is made of crust, mantle and core as its main divisions. Each of them have distinct characteristics. To understand their distribution based on density, the word isostasy is used. Isostasy refers to the state of gravitational equilibrium between the Earth's lithosphere as well as asthenosphere, where the lithosphere floats on the more ductile asthenosphere. Isostatic adjustment is the vertical movement of the lithosphere in response to a change in load such as glacial melting, erosion, sediment deposition or tectonic shifts. A classic analogy for isostasy, just like an iceberg floats with most of its mass hidden beneath the water. The Earth's lithosphere floats on the denser, more fluid asthenosphere. The taller the mountain, the deeper its root, which extends into the mantle, and this is similar to how most of an iceberg lies below sea level to maintain buoyant equilibrium. This illustrates the principle of buoyancy that underlies Airy's model of isostasy, where variations in topography are supported by differences in crustal thickness. This explanation captures the essence of isostatic compensation and how differences in elevation are supported by variations in lithospheric thickness. If you look at the continents which are thick, less dense, continental crust floats on higher and has deep lithospheric roots, that is approximately 125 kilometers, whereas oceans are thinner, denser oceanic crust which sinks lower and has shallow roots approximately nearly 75 kilometers. If you look at the mountains, they are represent areas with particularly thick crustal roots, much like tall icebergs. The theory of isostasy explains that less dense surface materials like seal float over denser interior layers like seema, with Earth's structure composed of concentric layers of varying densities. The core is the densest, that is 13.5 gram per cubic centimeter, and the mantle has intermediate density, that is 3.3 to 5.7 grams per cubic centimeter, and the continental crust is the lightest density, which is having about 2.7 grams per cubic centimeters. So, isostasy ensures a balance between these layers. So, this concept helps explain phenomena like post-glacial uplift as seen in Scandinavia, where Finland's raised beaches show a 250 meters rise over the past 8,000 years due to isostatic adjustment. So, following Pleistocene Ice Age. So, Pierre Bauer during his Andes expedition, that is in between 1735 to 1745, observed that the Chimborazo, which is the volcanic peak in the plumb line, did not deflect as expected. He concluded the visible mass of Andes has less gravitational attraction than what it should be. So, during the 1859, a team led by Sir George Everest had done geodetic survey of the extrapeninsular Indo-Gangetic plain, and discrepancies were found in the latitude measurements between Kalyanpur and Kalyana, that is 370 miles apart. So, these differences emerged when comparing results from direct triangulation and astronomical methods, indicating gravitational anomalies similar to those observed in other regions. Kalyana and Himalayas are only 96 kilometers away. So, 5.23 seconds was the difference between two results as given below, that is triangulation method which gave a value like 5 degrees 23 minutes 42 seconds. Astronomical method has given the value like 5 degrees 23 seconds 37 seconds. So, the difference between these two is 5.236 seconds. So, astronomical latitudes, that is based on plumb bombs and the stars, which differed from those measured by triangulation, especially near the Himalayas. So, this was attributed to the gravitational deflection of the plumb bob caused by the massive mountain range pulling it slightly towards the mountains. This led to early theories of gravitational anomalies and eventually to the concept of isostasy, as scientists realized the gravitational effect was less than expected, implying that the mountains had underlying low density roots balancing their mass. Let us have a discussion on concept of Sir George Airy. According to Airy, mountains are not hollow inside. Instead, their excess weight is balanced by lighter material beneath them. He proposed that the Earth's lighter crust, that is known as Sial, which floats on a denser substratum which is known as Sima, maintaining this isostatic balance. According to Airy, the Himalayas are not just surface features but extend deep into the earth, floating like a boat in denser glassy magma. The lighter rocks of the mountain sinks into the denser underlying material, maintaining isostatic balance. The Himalayas float in denser magma with most of their mass submerged, similar to how a boat floats in water. This illustrates the principle of flotation. An iceberg floats with 1 part above water and 9 parts below, illustrating the principle of flotation. So, similarly, if the Earth's crust has an average density of 2.67 and the denser substratum 3.0, then for every 1 part of the crust above, 9 parts must sink into the substratum to maintain isostatic balance. The law of flotation states that the freeboard ratio is 1:9. Although Airy did not use the iceberg example, he asserted that land masses float in the denser magma beneath, similar to how a boat floats in water. Applying the law of flotation to Airy's concept, the 8,848 meters high Himalayas must have a root of lighter material extending about 80,000 meters into the denser substratum, maintaining isostatic balance. The principle of flotation was applied by the Jolly to the Earth's crust with the freeboard to draught ratio of 1:8. According to him, assuming the part of the crust above the substratum as 1 and 8 part lies submerged beneath it. If this view is applied to Airy's concept, the Himalayas with a height of 8,848 meters would have a downward projection of 70,784 meters into the denser substratum. The Himalayas exert their actual gravitational attraction because they have a deep root of lighter material beneath them that balance their mass. He proposed that taller landforms have a greater portion submerged into the denser substratum, while shorter ones have a smaller submerged portion, maintaining isostatic balance. According to Airy, land columns such as mountains, plateaus and plains all have the same density. This means that the density remains uniform regardless of depth, and variations in elevations are balanced by differences in the thickness of the crust. So, Airy proposed that uniform density rocks make the continents, but their thickness varies. To illustrate this, he used iron pieces of different lengths in mercury. Each piece sank to a depth corresponding to its length. Similarly, wooden pieces of varying lengths placed in water also sank to different depths, supporting the concept that greater thickness results in deeper submergence despite uniform density. So, while Sir George Airy's concept of isostasy is widely respected in the scientific community, it has some flaws. Let us know that. According to his theory, every elevated landform must have a corresponding root of lighter material beneath it proportional to its height. If we apply the flotation principle to the Himalayas, their route would extend to a depth of 79,632 meters, that is with the ratio of 1:9. If you apply 1:8, that height should be 70,784 meters. However, such deep roots are unrealistic because they would reach zones of extremely high temperature, causing the lighter material to melt due to the geothermal gradient.